Hey, so that's nice. I want to give you some feedback on this Oscar, this confidence interval lab where you're guessing the mean age for the Oscar winners. So what I have here, I got a bunch of stuff in this Desmos sheet, but I wanted you to see just kind of the visual of what those last two questions were, like question 9 and question 10, where you are asking, is it possible for me to have two different confidence intervals with different numbers on the left and the right end and still be 95% confident that it's accurate? The answer is yes. And could they have two different intervals with 95% confidence that have two different left and right endpoints and then both contain the population mean? And the answer to that is also yes. Confidence comes from the area under bell curve. So some of you in your discussion were talking about confidence is just a feeling we get. How do I feel about this? And we're not talking about that confidence. We're not talking about how that feeling I have that I've prepared well for this test, so I'm confident I'm going to do well. That's not what we mean in this context. Confidence is a percentage between 0 and 100% that comes from an interval's width and the distribution of some sample statistic, not necessarily the mean. And we're doing the means here on this example, but you also do proportions in your homework in this chapter. But we're talking about means here, so it is means. So this is a theoretical curve. Okay, so if you give me a population mean, so I have a population mean here. This is the mean age of the Oscar winners at the time that I made this video, of all of them. So this is the mean age of all of them. And because that's the mean age, if we make the assumption that they are, even if those aren't normally distributed, if we made the assumption that the distribution of sample means was high enough, my sample size was high enough, they would be normally distributed, then I would have a normal distribution of sample means, and this would be that theoretical distribution of the sample means. Now, my sample size was only 10, so the central limit theorem doesn't apply, so we'd have to assume the distribution of ages of Oscar winners was normally distributed, which would not be a safe bet. Some of you actually mentioned that in there. So this would only apply when we have a distribution of 10 if the original population was normally distributed. So let's just make that assumption that they are, just so we can use that here. But this is a bell curve. This is this line down here. I'll move my head out of the way from left to right. These are sample means of size 10 of Oscar winners under the assumption that this truly is their population mean. It is their population mean. Again, I average this from my data set of the Oscar winners. So this is the population mean that I get. And so this is perfectly symmetric at this curve. So what this green line represents is 95% of all sample means that I could get of samples of size 10 of these Oscar winners would fall in this green interval. So that's the 95% right here. I'm doing the bounds and the inner. So the middle 95% falls between these two numbers, 38.8 roughly and 50.8. So if you guys made an initial guess in this range, when we did all that math that revealed if the interval was in there or not, as long as you were within this range with your guess, then you ended up hitting the population mean. But what question 9 and 10 said was, well, could it be possible for two different intervals to contain the population mean? And some of you even mentioned that, yes, I'm sure that other people guessed something other than what I guessed. And that's true. Almost all of you didn't change your guess to the sample mean, which you should have done. But yes, if I had different guesses, then I would be in different intervals. So here's what I want you to see, and here's why I'm making this. So this interval, this green interval, is the width in the population curve. Like this is the population mean. This is the length of the interval that contains 95% of the possible sample means. Only 2.5% are below this 38.8 number, and only 2.5% are above this 50.8 number. So what I have here down at the bottom of the screen is samples of size 30, just different sample means I could get from this distribution, with this mean and that standard deviation that we talked about. So these are different sample means that could happen if I had sample of size 10. Now we got, just so you can see it, we got, with our sample mean, we got 42.4. That's what a lot of you got that right. All you had to write was mean of that on that sheet, but we got 42.4, which is this number. I'll make it a little bigger so you guys can see it. Now, what I'm going to do now is I'm going to take the interval that contains 95% of the sample means, and I'm going to move its center from the population mean to this sample mean, right? And because this sample mean is in the 95% interval, when I move the center of the interval to the sample mean, the population mean is in the interval, right? I made this drawing on a lot of your pictures, and this is what I was talking about. This is the population mean. Because this girl over here is within the meter stick of the population mean, then that child that represents the population mean is within the same meter stick of that girl, right? This young man over here who's not in the interval, his meter stick doesn't contain the population mean. And that's what I'm trying to get you guys to understand here. Because this sample mean, the 42.4, was in the 95% interval of sample means from the population mean in the middle, then it too will, shifting it over to this confidence interval being constructed around the sample mean will contain the population mean. Okay, that's within the meter stick, so the population mean is now within the meter stick of this child. Okay, now I'm going to just briefly turn this off. That's the confidence interval. I'm going to turn that off. I'm going to turn off the sample mean that we got. I'm going to turn on all these other sample means. So these are 3 different sets of 30. And so you can see most of the time these dots are within the 95% interval. They should be, right? We're talking about the vast majority are going to fall in there. And you can see a lot of them are even clustered around the population mean. Sample means target the population mean. We don't see them far away very often, but this one's not. Okay, so when I turn this back on and I move my center of my curve over to this sample mean, you can see that the green interval doesn't stretch back to the population mean. If I center it around this sample mean, or if you think of it as a guess, somebody's guessed 52, then it's not going to contain the population mean. Right? The same with this one. This one's way out in the tail. It doesn't contain the population mean. But these, even though they're kind of far out, they're not that great of guesses, if you will, and they're samples that had some outliers in there, they do contain, if I pick that one, that sample mean, it does contain the population mean. The green interval does. All right, switching to the B, you can see the same thing. Most of these are within the interval. There's just one now that doesn't fall in the interval. So if I center it there and I turn off these, I'm not in the interval. Okay, and then the same thing with C. If I turn it on, I got one now down on the low end that is not in the interval. So because of that, it does not contain the population mean. Just barely misses it, but it misses it nonetheless. So that's the idea. Yeah, I can have all these other ones, if my sample means for any of these other values, they are going to contain the population mean. Okay. Now here's what you have to understand. Okay? And a lot of you were missing this when we were talking about in your discussion. I have no idea where this curve is. I have no idea what the mean is. And I have no idea what the bell curve is for this. I don't know. That's you guys before this started, before we revealed the bell curve. You don't know. I have no idea if I'm within it or not. Okay? I take a sample, I get a mean, I do the math to construct the width of this interval, I put the sample mean in the middle of the interval, and that's my guess for the population mean. I'm 95% confident it's in there. Okay? If I switch this from 95 to 90% confident, then this interval is not as wide. I don't contain as many values. Now I'm only 90% confident. I have no idea if I have it captured or not. And that's what I was trying to talk about to some of you with this process, is this person who has this as their sample mean. Right? And you can see that they do contain the population mean. They are just as confident as this person over here. This person that did not get the population mean in there, they're 95% confident the population mean is in there. This person is 95% confident the population mean is in there. This person is 95% confident the population mean is in there, as is this person. We don't know where this is. We have no idea. So the confidence is based on the interval, not the numbers. Notice that green interval is staying the same width the whole time. The number in the middle of the interval is what's changing. I'm not confident in the numbers. I'm confident in the width of that interval.